section. So it's a real pleasure to be here for the next, hopefully a bit less than an hour. I'm going to talk about a couple of topics. The first half roughly being about how to optimize complex metrics, and the second half thinking about how to pick good metrics. And both of these are ongoing work. I'm hoping both of these spark some conversations for folks here who might be interested in thinking about some of these questions, maybe pushing some of these ideas forward. Okay, so everything I'm going to talk about is with excellent collaborators. The first two, Gran and Cheyenne, were undergrads in my lab. They recently graduated. I moved on to bigger and better things. The second half is mostly with Garush, Shant, and Ruta, who are Garush and Shant being students at Illinois, and Ruta being a colleague, assistant professor at Illinois. Okay, so I'm going to just go right ahead and try to set the stage. I'm going to set up a cartoon problem where you're interested in building some kind of medical decision-making engine, so it's a medical classifier. This is very clearly going to be a cartoon, so there are lots of holes, many of which you're happy to sort of poke holes into the whole setup. But there's a particular thing I'm sort of interested in, and I'll try to hopefully flesh this out as I go along. Okay, so I'm interested in, say, predicting whether a patient has Alzheimer's or not. And I'm interested in this because I want to make a treatment decision. So I want to decide what to do based on my diagnosis. Okay, so I hire an enterprising young machine learner. They build some awesome model, and they get some pretty high accuracy. So this looks good. I feel like I've done a good job for the task. And one can imagine trying to use this directly in the decision-making pipeline, trying to use this to actually make a decision about a treatment decision. Of course, most of you should be very unhappy with this idea. There are many reasons for this, but at least one of them is that there is a ton of imbalance, we know, in population. And so it's easy to get high accuracy, but not to learn anything sort of meaningful or interesting about the task. Beyond this, when I'm going to make a decision based on my classifier, there are asymmetric costs. So the cost of treating someone versus not treating someone. So there are asymmetric costs in treatment. Okay. And so an interesting question as well is sort of thinking about how one makes decisions in a way that manages this asymmetry. So let's just go back to the sort of issue with rates. So these are semi-real numbers. It's sort of easy to come up with a cartoon and work this out. But based on the population prevalence and based on the accuracy, you can sort of show that the false positive rate of a classifier like this can be as sort of high as 90%. So this is when the model predicts healthy when the patient has Alzheimer's, and the opposite, when the model predicts Alzheimer's when the patient is healthy, can be quite low. So number of errors, the fraction of errors that the model makes in this setting. Okay, so you've sort of learned a little bit more about modeling. You look at these asymmetric, these bad rates on sort of different chunks of predictions, and so because of this, you decide that you don't like neural networks, and so you want to use a different model. So say you use a sort of nearest neighbor kind of classifier, which is my best approximation of a nearest neighbor classifier. And so, again, you look at the results afterwards. A little bit worse, but maybe that's fine. And then the false positive and false negative rates change quite a bit. So you're a little bit better in false negative rates, even though you've lost quite a bit in false positive. And so there's a different trade-off, different decision that you end up making here. Okay, so I'm going to just keep this going, because why not? 50 of these. So now I have a support vector machine. Again, different prediction accuracy, different trade-offs in terms of false positive, false negative rates. There's a fun one where I always predict healthy for everyone. If anyone remembers the numbers at the beginning, or maybe someone can guess what might happen in this setting. Okay, so yeah, so you end up with some like real high accuracy, in this case 99%. And again, the obvious reason is that there's a very low prevalence of this disorder in population. If you build a decision-making engine, not accounting for sort of all the steps that go in, you end up making a prediction that seems reasonable from a model point of view, but maybe not a good one. And so the question that comes up from all this is, of all of these models that all have different kinds of errors and different trade-offs in their error-making profile. Which of these models is sort of the right model to pick for a certain decision-making task? Assuming, again, I'm caveating a bunch of things. I'm assuming that sort of the ML model is plugged in right into a decision-making process, which you probably shouldn't do right now for most things. But anyways, okay. So this gets tied into, I think, a slightly subtler question, but a very important one, which is thought about in machine learning broadly, but mostly by subcommunities, and I think not so much by the broad ML community, which is thinking about how one should measure how good the model you're building is. How do you measure what good performance is? And like all good questions, I have a great answer. So the answer is it depends. So I don't have clearly there isn't a simple, clean answer, unfortunately for this. Because it depends on what you're hoping to use the model for. Depends on the relative costs and benefits of sort of whatever the downstream task that you're interested in. And so one way to try to quantify measurement of performance of a model is generically what is known as a metric. And I'll just dig a little bit more into this metric idea and talk a bit about some of the work we've been doing, thinking about metrics for primarily classification problems in machine learning. Okay. So a pretty important object when thinking about classification in particular is the confusion matrix. This should be familiar to most of you, and I alluded to this at the beginning. So just a quick summary. So what the confusion matrix tries to capture is statistics of different kinds of errors when you're making predictions. So on the sort of the top here, I have the ground truth, which in the binary setting is either 1 or 0. And here I have the prediction, which is going to be either 1 or 0 for every instance. And the 4 numbers tell me sort of how the fraction of times I either, the first box, true positive, I predict positive when the ground truth is positive, or I predict negative when the ground truth is negative, and sort of the 2 errors that I can make. So I apologize, true positive, true negative, and then 2 errors that I can make, false positive and false negative. And if I'm interested in accuracy, then the thing that I'm measuring is roughly trying to average the diagonal. So you can show fairly easily that accuracy is the average of the diagonal of the confusion matrix. So it's the average of the true positives and true negatives. Or error sort of is just the average of the off diagonals. So again, average of the false negatives and false positives. But beyond basic accuracy, if I'm interested in sort of other ways of quantifying or measuring performance, you can write essentially you have to work pretty hard to come up with a metric that can be written as some function applied to the confusion matrix for classification problems. And again, I'm happy to talk offline, but it boils down to the discrete nature of the decisions and the discrete nature of the sort of sample space. And because of that, the sort of mostly in the binary setting, there's sort of 4 ways things can happen. And so everything ends up being summarized. Even fairly complex metrics can roughly be summarized by some function of the confusion matrix. Okay. So as outlined, metrics are used to compare classifiers. We're going to talk a bit about how to try to optimize them when they're potentially complex. I guess a bit of an aside, but it'll come back later, is that these are thought of as population properties. So thought of as expectations with respect to whatever your data generating distribution is. But clearly you can approximate these from data. So you can count the fraction of times your classifier predicted 1 and the ground truth was 1. And this gives you an estimate of the true positives, for instance, as opposed to the actual, whatever the population quantity is. Okay, hopefully so far so good. Okay. So as you might imagine, there are a lot of metrics. So sort of each field often spends a bit of time coming up with what they think is a good metric for their area. And this is only, I'm showing here only sort of classification metrics. And as you might imagine, this is a tiny, tiny subset. I'm aware of at least one paper that's entirely a metric paper. It's just essentially a list of metrics and some thoughts on when they might be good or bad. So it's a fun process to come up with good measures potentially for some task that you're interested in. This begs the question, if I come up with some exotic complex metric, how do I come up with a good procedure for optimizing it? So the talk today roughly has 2 parts to it, as I outlined at the beginning. before the mic came on, so maybe this is good. Got a chance to repeat it. So the first part is thinking about how to optimize complex metrics. So I give you some metric that happens to be not as straightforward as an accuracy metric. Are there good strategies for trying to come up with a good optimizer? So a classification procedure that has good statistical properties for that complex metric. And the second part, I'll reverse the question a bit and talk about a bit of a new problem for us, but one that we think is quite important, which is, given some new problem, have to think about how to measure what good performance is. And we're going to reason about one strategy, which we think is sort of a reasonable first step for thinking about how to come up with new measures or good measures for estimating performance of a classifier, but one that is tied to the task that you're interested in, as opposed to something generic that you pull off the shelf. Okay, so I'm going to channel a bit of web spam. You might not remember this, but this used to be a thing. It might still be a thing. One simple trick on many websites. The first part of this is going to roughly boil down to a fairly straightforward procedure that works pretty well as a generic approach for trying to construct classifiers that optimize complex metrics. In order to set this up, I'm going to take a half step back, and instead of thinking just about binary classification, I'm going to expand the space a little bit to think about multi-class classification. From binary to multi-class is fairly straightforward in terms of, here I'm looking at the confusion matrix. So again, I'm measuring statistics of different decisions versus ground truth. In the binary case, it was 2 choices. In the multi-class case is some k number of choices. So the ground truth is 1 through k. I'm using 1 numbering here. And the prediction is 1 through k. And every pair gives me some number that tells me the fraction of times the ground truth is a certain prediction. And the ground truth is a certain value, and the prediction is a certain value. And so you can, again, get this measure of what the model is doing based on these statistics. And as you might imagine, accuracy takes the same form. So again, accuracy is just the average over the diagonal of this sort of more complicated thing, but it has the same flavor. I write this because this is going to come back. I'm going to think about accuracy in friends as essentially linear in terms of confusion matrix. So linear being broadly trace A, C, A transpose C. It's usually symmetric. If I write this, hopefully you can see this. This is what I mean. So sort of just thinking about this as a linear function of the confusion matrix. So element-wise product, sum it out, essentially, is what this comes down to. Sorry, I didn't hear the question.
What is trace?
Oh, so trace is the sum of the diagonal after the product.
Okay.
Yeah.
So transpose A, multiply by C, and take the sum of the diagonal.
Yes. Actually, okay, yeah. You don't need to do the trace here. So here what you want to do, I apologize, I made a mistake here. So here what you want to do is multiply the two. You can do it a couple of ways. So you can do a matrix multiplication and then compute a trace. Or you can do element-wise multiplication and then sum over all the entries. And both of those will get you the same answer. So either way, it's fine. The trace is the sum of diagonals of whatever the product in the inside is. Okay, other questions? Yes.
You mentioned symmetry, but open A is not symmetric, right?
Yeah. So I mentioned symmetry because I guess it may be many times. Nothing changes if it's not. So it's the same definition. Mostly what you want to be able to do is reweight every error in some way. And so the entry of A should just match the reweighting that you're doing. So if you do transpose, then you need to match. So maybe I should take out the transpose. The details here are not important. What's important, and thanks for pointing out, I guess, my sloppy notation, is that you want to be able to do this. Sum over ij, aij, cij. So that's the key thing. So you want to be able to reweight every kind of sort of error statistic that you're getting. And this is thought of as the simplest case, and we'll expand a bit to more complex cases. Okay. Does that answer? Okay.
Are you limiting the discussion to linear metrics?
The beginning will start with linear, and then I'll expand to more complex settings. Okay. Other questions? Okay. So, no trace. Okay. Good question, no? Okay. So, what do people do in practice? So, in practice, people mostly ignore the particular sort of. So if you read a sort of standard machine learning paper, what people do is construct some kind of model for solving a certain task, then evaluate it on sort of 10 different metrics, and not necessarily tying the task that they're interested in with, or the model that they're building with the measure that they're using. And this may be a good strategy, but I'll argue that you can do something maybe a little bit better. And so the standard strategy, say for multi-class classification, is to first construct some kind of score function, almost always. So logistic regression, random forest, some kind of neural network. And then your classification just becomes the maximum score out of sort of the list of scores. And again, this is sort of the standard approach that you would take to trying to build a multi-class classifier. And what I'll argue, it feels trivial if you followed me so far because it's the obvious thing to do, but I'm arguing this because it's actually not done very often, and again, this feels like a sort of cheap, easy thing to do to help you predict sort of more or get better predictions. If your goal is some, so for now, just think about the linear case. So I just have a linear weighting of the confusion matrix as my metric of performance. A better strategy is, again, the first step is the same. So just estimate some kind of score function. But instead of just picking the max, what I want to pick is some kind of weighted max, where the max is weighted by this reweighting, essentially. And you can show that the sort of Bayes optimal classifier for this metric, when I have a reweighting of the confusion matrix, boils down to reweighting the scores. So instead of just picking the max, what I'm going to do is for every choice, I get a list of weights. I reweight, I multiply them out, and I pick the prediction that is maximum over all of these choices. Okay, so fairly straightforward procedure, but I think something that is cheap to do and can lead to much better performance in practice. So to drive this point home, I will do a sort of quick simulation experiment. So suppose I just sample data from, in this case, it's just Gaussian normal data pushed through a logistic function. And the metric that I'm using is based on, just to make analysis simple, there are going to be two parameters that matter the most. One parameter is this D2, which is tied to the skewness of the A matrix of the reweighting. So I'm reweighting class by class. This A matrix is of the form sort of A11, A, K, K, and 0 elsewhere. So I'm just, some classes are more important than others, essentially, is what's going on here. And the D2 is capturing how skewed the reweighting is. So if D2, depending on how I choose D2, I either have sort of almost uniform across classes, or I can make it so that one class is hugely more important than the other one. Again, as a cartoon example, just to illustrate what's going on here. And then the other parameter that's important is WK, which ends up controlling sort of the skew of the score function. So again, depending on how I tune this, I can either have a score function that roughly has equal probability predictions for all the classes, or a score function that sort of predicts one class much, much more than the other classes, modulated by the Gaussian underneath it. Okay, so I can set up this simple experiment, generate random data, fit some logistic regression model. It's sort of the right model class here, so that's not going to be an issue. And then I can try to look at what happens if I either use the generic strategy of not bothering about the reweighting, or using the strategy that uses the reweighting in the decision-making procedure. And the results are mostly predictable. So the way I'm going to measure results is the performance ratio. So it's the ratio. Go ahead.
Quick question.
Yes.
On the previous slide, the WK is that the generative model you're talking about, or
Yes.
the model you're fitting?
This is the generative model, and I fit a logistic to it. So
Okay,
the
so
score function.
Direction is the same for every class. Every
Um,
class has the same direction with different magnitude.
Yes. The main thing I want to control.
Like very
Again, this is a cartoon.
strange problem.
Yeah. The main thing I want to be able to control, and the thing I'm trying to get at here, you can replace this with other models. The thing that I want to control is P of y equals k given x. And I want to control how uniform this is over the x's, or how skewed this is across k, so across the different classes. Whether this is sort of roughly equivalent for every class, so they get predicted at fairly equal fractions, or it's very skewed. So one class gets predicted much more than the other one. That's the important point here. Everything else is just...
Okay, so it's essentially a 1D classification problem.
Yes. But again, I want to emphasize that the point is to play with the skewness. So from the point of view of from the population point of view, the sort of specifics of the generative model are not critical. The thing, again, that I'm trying to make sure I capture is what's going on at the conditional distribution level. So if you like, you can use a more complex generative model, as long as you can. I want a simple experiment that allows me to control the skewness of the conditional probabilities and the skewness of my reweighting of different classes, and that's sort of the key idea here. Everything else is interesting and is worth exploring, but I want to think about that as sort of maybe less important as the main story. But good question. Okay. Other questions? Okay. So I'm controlling two things, and I want to see what the effect is. And again, this is a made-up problem. But the point made here is, if you know how you're weighting classes, use that information in your decision-making procedure. That's all I'm saying, essentially. But saying it in a convoluted, messy way. But that's the key point here. So I'm going to measure how good the model is by the ratio of what happens if I actually apply this weighted preprocessing, knowing the measure, or the reweighting for the classes, versus if I just pick the most likely class without taking into account the reweighting of the different classes. And the main takeaway that I want to sort of show here is that in terms of the metric of interest, or in terms of the final task, in this setting, again, this very toy cartoon model setting, I see up to sort of 5 times better performance by incorporating the reweighting into my classification procedure than if I just pick the most likely class without incorporating this sort of the weight, how important different classes are in terms of how I pick my model. Yes?
And your performance here is the accuracy?
So the performance here is the reweighted accuracy. Because again, the goal is, the target problem is the reweighted problem. And so the question is, do I bother reweighting in my classifier if I'm interested in the reweighted problem or not? Again, it feels obvious in this room. But I will bet you that most papers, even if they have a sort of reweighting previously specified, don't bother to sort of build that reweighting into how they tune their classifier. That's mostly what I'm trying to say here. Okay. So the point of this slide is that, again, it's a simple strategy, but it can have a big effect. So if you know how important, or you have a weight for different classes, use it in the way you're building your predictor. It's a cheap thing to do, and it can sort of improve your prediction by a lot. Okay, so you can do similar things, and I won't go into a ton of detail because it can get a little bit technical, but I'll give sort of the highlights of this approach. But you can do a similar thing for general metrics, so not just for reweighting, so linear measures. You can do this for sort of nonlinear measures as well. So F measure, like a ratio type function, many other kinds of function classes, you can do a similar kind of strategy. The setup is very similar, sort of 2 steps. The first step is you estimate some score function. At a high level, theory says as long as you have a sort of calibrated score function, you're fine. The real conditions are a little bit weaker than that. And then you're going to need to find a reweighting matrix and then reweight your prediction based on that reweighting matrix. And I'll try to give some examples and then some sort of high-level ideas of what this reweighting matrix might look like for more complex measures in a few slides. Okay. So again, if I give you some arbitrary measure, there exists a strategy for sort of most measures that looks like estimate the score function and then reweight the score function in order to find a good decision maker. So for sort of probabilists, maybe Bayesians in the room, this is effectively the Bayes optimal, a plug-in Bayes optimal predictor. So the Bayes optimal predictor looks like score function reweighted somehow. I am estimating the score function and then estimating the reweighting, combining them together, and I can show that this has sort of good statistical properties. Okay, so you can do this in lots of settings. Us and others. So we've looked at this for binary classification. Forgive my animation. I needed a slider animation. This was the only one I could think of. Classic old school animation. So we've done this for binary classification. So we talked about that already. Single confusion matrix. Multi-class classification we just talked about as well. So K classes, K predictions. I'm looking at the trade-off and statistics. You can do this for multilabel classification. So this is the case where I'm making multiple binary classification decisions simultaneously. And then you can also do this for what we've called multi-output classification. I'm making multiple multi-class classifications at the same time. And roughly the strategy doesn't differ that much. There are details that are different for different settings, but it's a sort of very similar kind of idea. Okay. So I'll also touch on a bit of a real application. So here's an application to recommender systems. So I have users and have items. Users rate some subset of items. I'm interested in predicting sort of the rest of the matrix. I want to predict the ratings of the users and other items, essentially. I'm doing this in a discrete setting. So this is a setting where the users give actual ratings, 1 through 5, 1 through 10. Some of us may have been doing machine learning where this was a problem that lots of people thought about in the research. But anyways, so this might be a good flashback for some people here. Anyways, so I predict 1 through 5, 1 through 10. And what I'm interested in is trying to find a good predictor simultaneously over items for all the users. And I'm going to do this by predicting the score for every user and then sort of finding a procedure to decide what to predict across all different items in terms of did they rate this item a 1, 2, 3, 4, 5. And in terms of how I'm going to measure performance, a good measure here is an ordinal style measure. And roughly what it's trying to do is the cost of predicting 2 when the ground truth is 1 is less than the cost of predicting 5 when the ground truth is 1. So you want your measure of error to sort of scale with how far away you are from the user prediction. Right? And so this is how you construct your reweighting matrix. So it sort of penalizes you making bad or predictions that are farther away from the ground truth. Okay? And so this is a problem setting. What we did here is that we looked at an existing model, a probabilistic model for sort of ratings prediction. It's called ORDREC. I think it won the Best Paper Award at Rexis that year. It's an excellent model. It does something interesting. The main thing that it does is that it tries to build the ordering into how it builds the sort of probabilistic prediction. And so the scores have sort of ordering prior knowledge built into them. And so it's a good model for predicting ordering. What I'm going to show is, again, to drive home this point, is I can consider 2 strategies. I can take the ORDREC predictor, which knows that I care about ordering, and just use that as my final prediction. Or I can take the ORDREC predictor, post-process it using this sort of linear reweighting, and then use the linear weighted predictions as my final predictions. What I'm showing here is, again, even if your model knows about the structure, using it in the sort of final prediction procedure ends up gaining you something in terms of performance. So we show sort of non-trivial performance gains. Again, I'm dating myself a little bit, but in this world, those numbers are quite meaningful in terms of the gap. Showing improved performance just by adding the sort of final post-processing that reweights based on how I'm scoring the final model. Again, I want to build a score such that it penalizes faraway decisions much more than close-by decisions. And that's sort of all that I'm building into this model. And again, most papers would not bother to do this. They would just use, because the model has all the structure built in, you just use that model to make a prediction. And what I'm advocating for is, well, if you know the score and you have some kind of score function that you expect to have sort of good calibration properties, then you should actually build that into the way that you build your final prediction. Okay, yes?
Could you, to an untrained eye like mine, there's an improvement, but how significant is the improvement when you compare that to the task that the classifier is meant to be doing?
So I think the point here is trying to tie your procedure to the task that the classifier is meant to be doing. So again, we chose the task to be make a prediction such that you minimize this ordinal score. You can replace that as, instead of using that measure, you could choose something else that you think is more appropriate for your task. And the point of this whole setup is whatever measure you pick, you should pick a sort of prediction procedure that is tied to that measure that you're interested in, as opposed to some generic one. So I don't know if that answers your question, but. Okay, maybe you can expand a little bit. I might have missed what you're
trying to get an idea of, how big was this improvement in this particular case? I mean, it seems there's some number, but
yeah,
it's a big improvement given that, and probably a tough case given that you had prior information in the score function before.
Yeah. So for folks familiar with this literature, this would be considered a non-trivial improvement because sort of at least for the standard data sets, it's hard to squeeze a bunch more out of the performance. I think my takeaway is you're leaving something on the table. It may not be a ton, but it's sort of non-trivial amounts of sort of performance gain for the task if you don't do this tie-in between the task and the prediction model. But I think that's a fair question. Yeah. Yes?
Is the model giving you a distribution over the ratings for one item, or is it giving you a joint distribution of the ratings of all unrated items?
It's giving you a rating for every item distribution over, so for every user item pair, distribution over the different scores. So 1 through 5 in this case.
So then it's not really being treated as a multi-output problem, it's just a multi-class classification problem. Is that right? So
it's being treated, there's a bit of nuance in your question, which is possibly best done offline. But multi-output in the sense that I am predicting multiple items at the same time. I think you're alluding to correlation, maybe?
There's no correlation then. It's
yeah.
The same as
I will, so you can define multi-output problems. So there is correlation in the sort of ground truth. This model is capturing it conditionally based on the sort of underlying structure. In particular, I didn't mention this, but there's low rank structure underneath the model that captures correlations between users and items. So the model is capturing correlation to some large extent. I can spend an hour talking a bit more on multi-output, so I will defer to maybe, if you don't mind asking offline, and we can expand on this a bit. But I'll just broadly say that there's correlation here, so it's sort of a standard multi-output. You can consider this as a multi-output problem. Or I'll say by fiat that you can consider it as a multi-output problem, and then if you don't believe me, we can chat offline. Okay. Yes?
Quick question. How is this metric related to the metric you defined in the previous slide?
Yes. So this metric is related because, or in a way, I could actually be more specific. The A matrix will look like, so if the ground truth is 1 and you predict 2, it'll be sort of 1. Ground truth is 1, you predict 3, then it's 2. Ground predict 1, you predict 4, it's 3, and so forth. And fill out the rest of the matrix based on the gap. So it's Aij is I minus j.
Right. This one is the lower the better, right? Yeah.
So
but here on the slide, you're saying that the higher is better.
I did 1 minus. I apologize. Yeah. And yeah, I should have clarified.
1 minus the metric.
So I turned it from a error to a utility.
But it's not necessarily normalized, right? It can be as high as 4.
Tell me what you mean by, I'm missing what you're saying. Let's go back to the previous slide.
If you predict 5 when it's 1,
Mm-hmm.
then this metric can be 4.
Yes.
But in the next slide, you have a metric that looks like it's somewhere between 0 and 1. So
Yes.
I'm not sure how the two are related.
I'll have to double check the details. It's a really good question. It's normalized to switch it from a utility to a score. It won't be 1 because of the point that you just made. So I made a mistake in the description of the metric. The normalization should be the maximum difference, roughly, and sort of rescaled so that it's between 0 and 1. I will double check the specific metric and let you know.
But
That's
you
a
want
good question.
to optimize the final metric, right? Not this metric.
I wrote it this way. In fact, I remember what it is now. It's 1 over, I apologize, 1 over k. So it's normalized to based on scale, and then because I want to focus on the utility, I do 1 minus. And I think this is the metric. Thanks for jogging my memory. So the normalization makes sure that big things and small things roughly 0 to 1. And then because I like to work with utilities instead of losses, I do 1 minus. And it's common in this setting as well. Okay, good question. Other questions? Cool. All right, so let's move on a bit. I'll talk a bit about why reweighting works. And for thinking about reweighting, I think it's useful, and the way that we came up with this strategy and others that have looked at this problem is instead of thinking about it in terms of classifiers, sort of take a step back and think about it in terms of confusion matrices. And that seems to be the right abstraction for classification problems. Again, because for most problems, you can abstract them out into just reweighting in some way these kinds of error statistics. Okay, so specifically what's going on is that I can actually map out, if I take a particular problem, assume some generative distribution, I can map out all possible classifiers. It's hard to do. But you can characterize the space of sort of all possible confusion matrices for a certain problem setting. If you're familiar with the RLC curve, it's effectively the RLC curve for this top portion. So this part is the RLC curve for that problem. And then for completeness, you can also sort of flip it around and intentionally make bad decisions. So flip every classifier to make more negative and positive. And you can map out this sort of the other side, the negative side of the RLC curve. It has some nice symmetry properties, which are actually kind of fun geometrically, and happy to chat offline about those. But anyways, if you map out the space of all possible confusion matrices, you get a lot of actually really interesting geometry. In particular, the space of all possible confusion matrices ends up being a convex space. And because of this, it ends up, in terms of characterizing what good classifiers are, it ends up giving us a little bit of insight, which I'll try to briefly outline here. So to make the discussion easy, I'm going to focus on metrics which we've roughly called monotonic metrics, which are metrics that reward you for making good decisions. You can construct metrics that don't. It's probably not a good idea, but if you're flexible to do whatever you want, you could do it. If you use a metric that rewards you for making good decisions, roughly the metric is going to be monotonic in this space. In particular, the gradient field is going to be sort of up and to the right somehow. Angle might be different. It might be a bit of curvature, but roughly up and to the right is a good thing. And so just by analyzing what's going on between the metric and the space of confusion matrices, it might be obvious to you already that if my metric is monotonic, then the optimal must be somewhere on the boundary. So the best confusion matrix out of all the possible confusion matrices for this particular metric must be somewhere sort of along this boundary of confusion matrices. And boundaries are nice because boundaries have nice properties. So boundaries of convex sets in particular, you can construct a support function, which is just the tangent plane, at that boundary point. And so what this means is that you can show that if a metric is monotonic, then it must be optimizable by this sort of plug-in reweighting strategy that targets a boundary point. And the question now becomes sort of which boundary point should I target, or sort of what this line is. And for linear problems, it ends up being easy. It ends up being essentially just this reweighting matrix. For other kinds of problems, it ends up being a bit more complicated. But you can show that the optimum is given by the gradient of the loss at the best possible confusion matrix. This is a weird problem because in order to find this tangent plane, I need to know C star, the best confusion matrix. In order to find the best confusion matrix, I need to know the tangent plane. So it's a bit circular. In practice, there are sort of good empirical procedures for trying to estimate what a good boundary point is using plug-in procedures. And I'll talk about the binary case, and I'll defer offline to sort of other cases. One nice thing I should also mention is that this characterization is exhaustive. So this rough property of sort of being optimizable at the boundary characterizes it goes two ways. So from one point of view, it tells us all the classifiers that can be optimized by this reweighting strategy. So optimized in a certain sense, meaning the strategy that I come up with will be consistent. So in large sample limits, will converge to the best possible classifier, the Bayes classifier in this setting. It also says sort of roughly the other as well. So if a classifier doesn't end up on one of these boundary points, then the reweighting strategy will not work. It's possible to come up with other strategies for doing it. For 99.99% of the cases, it's not necessary because, again, we almost always use monotonic functions because we like metrics that reward good predictions. So this is a good enough characterization for almost every case that you'll come up with. Yes?
Sorry, this is maybe a very silly question, but so this optimization of C star is in terms of the performance of the accuracy as you described it before.
Yes.
But at the beginning of the talk, you also alluded to sometimes choosing a specific true negative or true positive fraction being more suited to a specific scenario where the costs drive the definition of your classifier.
Yes.
And so just wanted to make sure that those two could be different points on the RC curve. Right?
Yes. So I guess to expand a bit on your question, I'm assuming that I think it's a fair point that you're bringing up. But I'm assuming that for every problem that you're interested in, you're focused on characterizing things in terms of some function of asymmetric decision costs. What's the actual... so the question of picking particular points along the performance surface at which to predict, I think is an interesting question. There are ways to do it. I'm not talking about them here. I probably made things worse by trying to describe this sort of metric selection problem in terms of picking an operating point. What I was trying to express was that there are asymmetric trade-offs and potentially complex trade-offs in terms of different kinds of errors. And that's what you want to capture using your metric. That's what I was trying to say.
Thank you.
Okay. So as I mentioned, so you can show that this overall strategy is consistent. Again, it's a bit abstract right now. I'll talk about the concrete case of binary classification in a second. But roughly the idea is estimate a score function, figure out this magical B matrix, and then based on the score function in the B matrix, use that to come up with a good classifier. And so in particular, with binary classification, you can use a similar procedure. One nice thing about binary classification is that you can show that the degrees of freedom in the A matrix actually boils down to just a single number, essentially, which is effectively where am I going to put my threshold in this binary classifier. And so the strategy now becomes estimate the score function, estimate a good threshold based on validation data, and then make a prediction based on that thresholded score function. So the main difference is that instead of thresholding, for folks familiar with this literature, for accuracy, you always threshold at a half. For more complex settings, you threshold somewhere else. And the threshold is tied to the sort of metric that you're interested in optimizing. And you can show rates for this. So roughly under weak conditions, I think the main thing to keep in mind is that you pay a log n cost versus if I knew the threshold ahead of time. So if I was interested in accuracy, you can get sort of order 1 over n. And here I'm paying this extra log n factor because I have to find a good threshold in addition to sort of finding a good score function. Okay, so that's that for the first part. In the next 10 minutes, I'll very quickly talk about how to pick metrics. So again, a quick reminder, there are lots of metrics, even in the binary classification case. There are lots of metrics in other cases as well. I'm showing, just motivating from recommender systems, the point that metrics are not always exchangeable in the sense, exchangeable has a technical meaning, but what I mean here by exchangeable is that optimizing one metric doesn't necessarily do well on a different metric. And here's a sort of real-world example from a paper thinking about optimizing top-end accuracy based on a procedure that was very common there, which is, if anyone remembers the Netflix problem, everyone was thinking about minimizing RMSE. And the sort of main statement in this paper is minimizing RMSE doesn't necessarily give you good top-end performance. Again, 2 different metrics, optimizing for different things. The performance of the sort of different metrics are not necessarily the same. Regardless of this, as anyone that has played with particularly applied problems will know, is that you really can't easily escape thinking about how to measure performance. So in addition to sort of picking model classes, optimization, thinking about how to get your data, an important part of the ML pipeline is thinking about how to measure performance. And that ends up affecting, or should affect, sort of the rest of the whole process. So you might want to ask how experts pick metrics. Lots of experts in this room. I'm going to argue for 99% of the cases, in academia anyway, people just use whatever is default in their field and just throw that onto the problem. In industry, it's maybe a bit more important to get things right, and so you might run some maybe tests or user surveys and maybe hire people to try to come up with a quantification of what good performance is for a certain problem. I have one controversial slide, which the main important part is this bottom thing. It's a suggestion by a fun colleague. Our metrics are just almost always just completely made up. So we've come up with a general framework that we're expanding on, and I'm happy to, again, talk a bunch more here. I'm thinking about this question of how can I elicit good metrics by interacting with either an expert or a population of users. The first problem that comes up is I need to quantify how good a certain model is. People are quite bad at sort of giving scores to models if I try to ask them. Usually they're a little bit better at doing pairwise comparisons. And so if I ask people, is a certain model better than another in a certain setting, or if I do an A/B test and I sort of measure a whole population, I can usually get a much better quantification.
Question?
Yes.
How do you even ask the question of the user? Like right at the beginning, you gave the example of 4 different ways of classifying Alzheimer's. And so maybe you're saying the model, this phi that you're asking these users to classify is characterized by the false positive and false negative rate. But in more complicated situations, it'd be harder to say even what are the things you're comparing.
So the setup we have requires that you roughly decide the set of things that you're comparing ahead of time. And what we're assuming is that there is sort of an internal trade-off function, but it's hard to turn that into math. And this is roughly trying to turn sort of internal trade-off function into math. There is a problem in the middle that we haven't fully addressed. This doesn't address, we're thinking about how to address, which is what you're alluding to, that we've pre-decided the set of things that we're going to trade off. And there might be a much richer space of potential things to trade off, including things that are not sort of easily captured here. We are still working on it. I don't have an easy answer for you. But we have an answer when I've decided ahead of time the set of things that I'm trading off. Okay, so the next point is that you want to minimize number of queries. So remember, we're asking real people. People are going to get tired if you ask them too many queries. And so the goal is to focus on sort of query complexity. So you want the fewest number of queries in order to get the answer that you're interested in. Okay, so I'm going to rush through a couple of things here. But it's maybe easiest to describe for binary classification. So in binary classification, again, as we talked about, weights are effectively linear functions. And so eliciting metrics is equivalent to sort of finding the right tangent plane that recovers what the oracle is interested in. Okay, so what I can do in order to solve this task is, and what we actually do is unroll this function. So in the binary setting, I can solve this as the following problem. I have a one-dimensional function. I don't know what the function is, but I'm able to ask pairwise comparisons. So if this is B and A, I can ask is phi of B greater than phi of A? Okay, quick question in half a minute. If I have this kind of problem and I'm interested in finding a maximum, what strategy could I use to find a maximum? CS 101. Bandit. You can use bandits, you can use easier things. So it turns out for this setting, it's enough to do binary search. So binary search is good enough and actually provably sort of optimal in this setting in order to find a maximum. Just doing, if all I'm restricted to do these comparison queries. Okay. So I'm rushing a bit to make sure I get done in time. I apologize. I over-budgeted at the beginning here, so my metric is a bit off. But so you can show some nice properties of this. In the linear setting, you can show that you can recover the oracle metric with sort of low error. In particular, you can guarantee epsilon error after sort of log 1 over epsilon queries, and you can actually show that you can't do any better without making much stronger assumptions in this setting. So it achieves the lower bound. And we've expanded this to more complex settings. I think for here it's sufficient to talk about the binary classification setting with linear metrics. And we can also show that the general procedure is quite stable to noise. So Oracle is not giving us the exact answer, or noise, or sort of other various sources of noise in this problem. Okay, so to summarize, hopefully I've convinced you, or at least intrigued you, that selecting good metrics is important in coming up with good machine learning models. We've roughly talked about two ideas. So one, sort of a plug-in procedure, given some complex metric, to come up with a good classifier that sort of is good for that metric statistically and seems to work quite well in practice. And the second part, I talked a bit about how do I come up with good metrics for a certain problem by interacting with users, with experts, and sort of other kinds of interaction procedures. So we're doing a bunch more work on this. We're thinking, I think, I guess at the end, I'll just mention that one area where we think this might have a fairly big impact is thinking about ML fairness, where quantifying exactly what you're interested in terms of the trade-offs can be quite challenging. And we think particularly the elicitation strategy might be a good approach there. And it's one of the things we're actually pursuing. And with that, I'm about on time, which is great. I'm done. Thank you very much.
And we do have time for one or two quick questions. Yeah.
So regarding the post-processing, have you thought about what kind of difference this might make to changing the reweighting, if possible, during training? I'm just a bit worried about a model which may essentially learn not to distinguish between what should genuinely be different classes, and that information will be thrown away so that your score won't reflect that. And then maybe some of the cases on the boundary would be reclassified correctly, but you could be missing out on a whole bunch of cases that have just been neglected by the classifier optimization.
Yeah, I think that's a important point. I would say everything we talked about here is plug-in style, meaning we're assuming that you first estimate a sort of prediction, probabilistic or score function model that roughly captures everything that you think that is going on in the data, and then we apply this reweighting as sort of a second step. So the particular issue that you brought up will not happen using the particular approach that we're using. Now, if you build in this reweighting into the learner, then it's completely possible that it will, for instance, ignore some classes if the score function says it's not important. I think, again, if the metric at the end doesn't care about a pair of classes, then I think it's arguable whether your model should be spending a lot of effort. Most rule metrics will not have this, but if your particular problem says cats and dogs are equivalent and I don't care about making errors between them, and the metric reflects the fact that there's sort of no error from, you don't get penalized for making mistakes between cats and dogs, then it's completely reasonable for the model to not be able to disambiguate cats and dogs. Because in the setting they decided and the evaluation that you decided, that's not a meaningful difference for you. Does that answer your question?
Kind of. I was sort of getting at the other direction. So suppose I'm training my model and my negative class is really, really rare, as in your example. Yeah. And I'm training that model with accuracy as its own like metric. That model itself, the model you get at the end, would just completely disregard the negative class, and no post-processing of the score is going to bring that back. So models are rarely trained. In fact, you cannot train a model to optimize accuracy. What you can do is some surrogate, logistic loss, squared loss, whatever. Sort of all the hard metrics, hard in the sense of discrete metrics, are NP for most function classes anyway. So we always use surrogates. I can chat offline. But roughly, most score functions that you actually use end up, I mean, they do a better or worse job about rare classes. I think that's a fair point. But they're almost all smooth surrogates. So they're not directly optimizing for accuracy. The accuracy part is often at the end where you then make a decision based on the score for your threshold. So that problem does happen, but a slightly different version from how what you described.
So let's end here.
Okay.
Thank you all so much for the fantastic questions. If you have any other questions you would like to follow up on, either on the material presented here or any of the other work that Sami has done recently, do catch up here either during lunch or in the early afternoon. With that, thank you so much for your attention, and thanks again, Sami, for a fantastic talk.
Thank you.